Okay, so welcome back, and we start this afternoon with the talk of Sidney Nagel on jamming. So.
Yeah, well, thank you very much, and I want to really thank the organizers for bringing me to this wonderful place to talk about some of the work we've been doing. In listening to all the talks, now it's on? Yeah, okay. Listening to all the talks so far, it's clear that these ideas of spontaneous symmetry breaking have a very broad appeal across lots of different areas. And this puts me in mind of this quote by the great philosopher Alfred North Whitehead, that a great idea is like a phantom ocean beating upon the shores of human life in successive waves of specialization. And I think that somehow captures something about what this whole conference is about, paying homage to these ideas of broken symmetry. And so what I want to talk about today is the idea of jamming and the idea of rigidity between two poles from order to complete disorder. And the first question that would come to mind, is there anything like this idea of perfect disorder? And what I want to first remind you of is, well, if you asked about what is perfect order, you would say a crystal is a perfectly ordered system. I mean, it's somehow the essence of order, that you take one unit cell, it's perfect, and you repeat it over and over and over again, interminably in space, and this gives you something completely ordered. And this is how we think about starting to talk about the properties of solids. So that if you take a solid, the first class that you take in solids, you begin to hear about perfect crystalline order, and you try to understand that and what it means. But if you ask, well, how about real materials? Well, real materials are never perfectly ordered. And so the next chapter that you would get into in a solid state physics book would be telling you, well, you can add defects one at a time, and you can study something about the properties of these defects. And, well, you can do that up to a certain extent, but then at some point, it doesn't begin to make sense anymore. When you start talking about a real glass, so a piece of window glass, for example, or a metallic glass where things are completely disordered, then it doesn't make sense to start at the perfectly ordered limit to try and get to the point where you can begin to talk about the properties of this glassy state. So you can't really perturb around the crystal by adding defects to get to the physics of glasses. And so what you would like to have is the other opposite extreme from order, that a place where you can start with complete disorder to try and talk about the properties. And then a real material would be someplace in between from order to complete disorder, so someplace in between that. And having both places is a good place to be able to, a theory that be able to, look from one side to the other to really begin to decide at what range do you want to start thinking about things, is it from the disordered limit or from the ordered limit? And so the other place that I want to start thinking about today is about jamming. And so what non-equilibrium process is it that would create something that has complete disorder? We know that the perfect crystal, you get to that by taking a liquid and you cool it down into a below its freezing point, and it nucleates and has a first order phase transition into the crystalline state. What do you do with a glass? How do you begin to think about that? And so what I want to think about now is how one might think of forming such a system. And so I want to start looking at it from the jamming limit. And so this idea of jamming goes back for about 20 years to a time when Robin Stinchcombe was working with us in Santa Barbara. And these ideas kind of stem from that period of time. And so it was very nice to be able to meet up again here. So the idea for the how to make a jam system is that you take a bunch of spheres, perfectly smooth spheres, you put them in a box, you put them in at random. So this is something as if you had infinite temperature, the particles can overlap, the interactions are just going to be purely repulsive. There's no friction, just purely repulsive interactions. So you put them in randomly into a box, and so here is in this box in a computer, and then you take this thing and you look at these particles and they're overlapping. There's a repulsive interaction between the particles, so they're going to push each other apart. And so they will keep pushing each other apart until they don't have any overlaps anymore. And at that point, the system is in its ground state because there's no lower energy it can get to if no particles are overlapping and we're at completely at t equals 0. So there are two possible things that you could have. Well, one is that the system has these there are no overlaps, but there's still plenty of space between the particles, so these particles could still move. And so that is an unjammed system. That is a system that you could just shear it and this thing would move easily. There'd be no energy in the system and there'd be no pressure in the system because there's no repulsive forces that are acting to actually push these particles apart. On the other hand, you could go over to here where the particles really then begin to start to overlap. And if they start to overlap, then they no longer can easily move past one another. And so they are pushing each other apart. There's an energy because they're overlapping, and there's a pressure because they're pushing out against the walls of the system. And so the kind of potentials that we're going to be talking about are really the simplest kind of thing that we can think of. You take a sphere, spherical potential, purely repulsive, and its finite range. That is, if the particles are outside their radius of each other, they don't see each other at all, but if they begin to overlap, then they will begin to push each other apart. And so it has a potential of this kind. So think of it as just springs, which are just repulsive springs up to a certain point. That is, if they don't pull each other back together again, they just repulsive out to that point of where they begin to overlap. So at some concentration of these particles, they will start to see each other. If it's too low, they can't see each other. If it's too high, well, then they are forced to interact with one another. And so you can ask the first question, which is, well, how do I go? Yeah.
Are all your spheres the same size?
They don't have to be. I mean, that's, so in this particular case, there are certainly two sizes. In this one, typically in 2 dimensions, it makes a big difference. 3 dimensions, it makes much less of a difference for what we're doing. But we can do, you know, typically we do very polydisperse systems. So in asking, well, what kind of transition is it that you go from one side to the other? You would say, well, look, could I have in the unjammed state 2 particles and only 2 that are overlapping? And we just answered that question. No, they can't be that way because they have to push each other apart. So you can't have 2 particles overlapping, but how about 3? So I have one here, my head, and I put another one here. Well, my head can't move, but this guy can move off, and then I can move off, so that I can't have 3 particles that are overlapping. And so I can keep doing this until I realize, well, the only way I can go from the unjammed state to the totally jammed state is when somehow I have interactions that span the entire system.
Do you conserve the volume?
Yes, so the volume here is fixed. We can do it in any kind of ensemble you want, but I'll be talking about a constant volume ensembles here. That was to wake you up, I hope. Okay, so so if I go and I decide that I'm going to have, that I have this change in the number of overlaps. At the unjammed state, I have 0 overlaps. In the jammed state, I have to have overlaps that span the entire system. Well, how many overlaps do I have to have? And this goes back to argument that goes back to Maxwell, where he was trying to understand bridges and whether bridges would collapse or not, and whether they'd be stable. And so he made the argument that you want to know how many degrees of freedom you have, and you want to know how many constraints you have. So in this set of n particles in a box, how many degrees of freedom do I have? Well, I have n particles, and if I'm in d dimensions, that means I have d times n degrees of freedom. How many constraints do I have? Well, I have all the particles that are overlapping with one another, and so each one of those is a constraint on the problem. And so I have n times z, which is z, the number of constraints. But remember, each constraint is counted twice because it's, this particle overlapping with this is the same as this particle overlapping with the first one. So I've double counted, and so I really have nz over 2 constraints on the problem. And what Maxwell told us was the minimal number of constraints that I have is when these two things are equal to get a stable system. And so when you have that, then you just set these two things equal, and that says the critical number of contacts you should have, that the critical coordination number, that is, z is the average number of contacts any particle has to be 2 times the dimension of space. And so in 2 dimensions, that would be 4. In 3 dimensions, that would be 6. Now, that sounds simple enough, but then you think about it for a second, you say, hey, wait a minute. I mean, here's my head, and I'm in 2 dimensions, let's say. I put one contact here, one contact here, and one contact here, and now my head can't move. That's only 3 contacts, and he just said 4 contacts. Okay, so what I just did for you here was a local constraint. That is, that was how many local contacts did I have to constrain this one particle here. What Maxwell was telling us about was the global constraint of the problem. How many does the whole system have to have at minimum in order to make sure that this thing is rigid? And so it's this difference between the local and the global, which is where I think all the bodies are buried in this problem in some senses. So how do you go from the local to the global and get these 2 different types of constraints to agree with each other and still stay rigid? So you have this jump in the coordination number from 0 to this value zc at this transition. And so it's every system that you do as you try and get this thing to jam will suddenly jam at this point where the coordination number is 2 times the dimensionality of space. So it's a universal number in that case. But if you go above that, because these are soft particles and you can continue to push these things so they will overlap with one another, you see that z minus zc continues to increase. So it isn't that it just stops at z equals zc, but it increases above that as a square root. And this is true in 2 dimensions and 3 dimensions. It's a general thing for all of these different dimensions, that this is, that the number above that constraint value continues to increase in a smooth fashion. So now I want to turn to the idea of rigidity here. And just to remind people, since we've been talking about all sorts of different things, some just simple things about rigidity, is that there are 2 kinds of things that I want to talk about. One is the bulk modulus, and the other is the shear modulus. These are 2 of the most simple kinds of things that you could ask about a solid. So what is the bulk modulus? The bulk modulus is if I take the solid and I try and squeeze it from all sides together, then I want to know how much energy that takes, and the amount of energy that takes is a bulk modulus. The other kind of thing, the shear modulus, would be if I took that solid and don't change the volume, but I just shear it without changing any volume, and then I again pay some energy to do that, and the amount of energy that I do there will be, again, the amount that I have to pay will be measured by what's called the shear modulus. And so one thing that you should kind of know about this is the shear modulus and the bulk modulus in crystals are always roughly comparable to one another. Maybe a factor of 3 different, but that's about it. They don't vary by enormous amounts. And why is that? Well, you have atoms in your crystal, And in, let's say, the compression, you're pushing them into each other. In the shear, you're trying to make them move. Did I? I try to move past one another. And in each case, I'm paying the energy of one atom moving into the potential of the other, and it's that same magnitude of that potential. In both cases, maybe they're off by a cosine theta, but they're both basically comparable to one another. So this is typically how crystals behave. And so just to talk about this for one more second is that you can take the shear modulus and the bulk modulus, and you can take the ratio of those two things. This gives you what's called the Poisson's modulus of the Poisson's ratio of the system. And the Poisson's ratio is this thing that is, if you take a piece of material and you stretch it like this, what you expect to happen is that it will shrink in the other dimensions. And that's a normal positive Poisson's ratio material. A weird material is when you pull it in this direction and it expands in the other two directions. That's a weird kind of system, and most materials are not have negative Poisson's ratio. They typically have positive Poisson's ratio. So being able to make something with a negative Poisson's ratio is considered kind of a weird thing. This is something that you would think, well, if we could do that, maybe we could make interesting materials out of this. And so the reason I'm saying that is that the Poisson's ratio is just a monotonic function of this ratio of G over B, and so I'm going to come back to that later in this talk. And so what I want to ask for this idea of rigidity, is does disorder matter? And so this is, I've told you about this for what happens in the crystal, what happens if I have a disordered system. So if I go back to the jam system and I just measure these quantities as a function of the distance from the point where this thing has just jammed, I can look at the pressure as it increases as I continue to compress the system, or I can look at the shear modulus as I compress the system. And what we see is two things. One is that they both behave as power laws above this transition when measure phi c, and the phi c is the same for both where the pressure goes to 0 and where the shear modulus goes to 0. So, and the bulk modulus is just a derivative of the pressure, so that again is also going to be a nice smooth function of this. And so what we have is a kind of a strange transition that I've just told you about. That is, we started with something. I told you that this coordination number is doing something strange, that it's jumping, that is, it's discontinuous at the phase transition as I go from unjammed to jammed. On the other hand, all these other quantities scale smoothly above that point. So z minus c increases at the square root, the pressure in the bulk modulus scale, and the shear modulus also scales smoothly above that point. So it's a strange kind of a transition. It's a kind of a mixed order phase transition where some things are discontinuous and other things are very continuous in this transition. And so this is one thing that for a conference like this is to try to understand, well, how do we put that into the picture of the spontaneous symmetry breaking in this case? And that's something that I'm not sure I have any wisdom on, but it has some relationship to what we've been talking about. The other thing that I want to say here is that if you look at what these power laws are, something strange is happening. That is, the pressure is doing exactly what you would have expected the pressure to do. As you compress it, it's going to just go linearly with phi minus phi c. Whoops. Phi minus phi c. But the shear modulus has an anomalous power. And it always seems to be this anomalous power. It's going as the, instead of the bulk modulus would be 2 orders of second derivative of the potential. This is a 1.5 derivative of the potential. That is, it's going much slower to, the shear modulus is going faster to 0 than the bulk modulus is. And so what that tells you is that as you go closer and closer to the transition, unlike the crystal where the system would remain roughly same amount of, the that if the shear modulus goes down, the bulk modulus would go down in tandem. Here what we're seeing is that as you approach this transition, the shear modulus is getting infinitely weak compared to the bulk modulus. And so this is a weird kind of solid, again, that you're getting to be able to play with. And so the question that I want to ask now is, well, okay, so I've shown you that something is different about the kind of rigidity in this system, that it's not the same kind of rigidity that we have in an ordinary crystal, but what else is distinctive about disordered matter? And so another thing is, what are the excitations? And so this is something that we've heard about in this conference as well. We know if you have a transition, you can try and say something about what these excitations look like. And the excitations in a solid are just going to be the normal modes of vibration, show just what kind of vibrations you have in the system. And so we know for a crystal that the low frequency vibrations are going to be very long wavelength plane waves. And it's just elasticity of this system. So the longer the plane wave, the lower the frequency that you're going to have. And we know how to count these excitations. These are just going to be how many plane waves of different wavelengths can I fit in a box. And so this is the standard calculation that led to, well, it's the bimodel for low temperature properties of solids, but it's really what Einstein was thinking about when he tried to first think about, well, what was quantum mechanics have to say about the low temperature specific heat. And so it all comes down to what does the density of states of these modes look like. So the density of states, how many modes do I have as each frequency, goes to 0 at 0 frequency. That is, if I have a box that's very long, I can only put in one long wavelength mode into that box. So there are very few of them. But if I have very short wavelengths, I can put lots of different directions of those modes into this box. And so the density of states goes as the frequency to the dimension minus 1, so omega squared in 3 dimensions. And this is perhaps the most robust law that we have in condensed matter physics. That is, it's very rare to see any kind of difference from this kind of scaling of the density of states, so the low temperature specific heat of a system. And why? As well, because if you have something that's got disorder in it, well, you have a long wavelength, and what the long wavelength does is it basically averages over the disorder in the system. That it doesn't, that if the wavelength is long enough, you're getting a very good average of what the elastic properties of that material is in each wavelength. And when this wavelength has that disorder, this next wavelength has comparable disorder, then the elastic properties are the same, and you go back to elasticity theory, or that you get plane waves. But what happens in a jam system? And so here is a perfect crystal. So this is the famous picture of what the vibrations are for an FDC crystal. You see, what I'm interested in is what's happening here at the low frequency end, and this is coming in as omega squared for an FCC crystal. What happens when I go to a jam system? Well, when I go to a jam system, everything is different. And so we have at high frequencies, the density of states falls off because there's the highest frequency in the system. But as I lower the frequency and I'm at some compression, you see it comes down and then it starts to fall off. But if I get a little closer to the transition, so I go from this red one here to the green, it looks like it's getting flatter and flatter at lower and lower frequencies. If I go down to the next red one here, it's almost completely flat all the way down. That is, at the transition, what this is saying is that the density of states is actually constant all the way down to 0 frequencies. It's not going to 0. What that means is that in this region, the amorphous system, this jam system, has many, many more degrees of freedom, many more excitations than does the crystal. So there's a whole lot more things that can happen here that could happen in the crystal. And so this is a new class of excitations that's come out of this kind of a picture of this way of creating a rigid solid. And so if you go to the transition, since the density of states goes down all the way to 0, that means that there is no place where, no length scale on which I can do that thing I just told you about, averaging, to get back to elasticity. So as I go to that transition, the length scale at which I have to average is going to infinity, which means that this thing is getting so disordered that there's no length scale anymore on which averaging would regain my elastic behavior. And so that's in that sense that I want to say that jamming really is the epitome of disorder. That is, I can't get any place that's really more disordered than that. So, so these are two things that have to do with how a jam system is different from the crystal. And now the question that I want to ask is, well, over what range do I care about jamming, and what range do I care about whether it's really an ordered system? And so there's a way that we can kind of look at this, which is on a computer where we put down a perfect lattice. So we start off with a perfect crystal. And now there are n particles, and I take m of them, and I remove them at random, and then I put them back at random. And so if m is equal to 0, that is, I take nothing out and I put nothing back in, then the system is a perfect crystal again. If m is n, that is, I take all the particles out and I put them in at random, then I have gotten, that's the original jamming scenario. So by choosing a ratio of m over n between 0 and 1, I can tune the system between perfect order and the complete jamming scenario. And I want to see over what range does the jamming physics come in, and over what range does the crystalline physics come in. And so we've done that here, and so this is a nearly perfect crystal. This is the jam system, disordered jam system, and in here is an intermediate system where we didn't take out too many, but you can see that there's, it really looks quite ordered. In here, you can see some of the red particles, which the color is trying to tell you how much disorder there is locally on the system. And you can see that this thing looks quite ordered if you were just to take a look at it naively. And so the question that I want to ask is, okay, so to what extent are these things going to be jamming or crystalline-like behavior? So in the two things that I talked about, first I'm going to look at what happens to the this ratio of G over B in these two cases. So in the case of the crystalline system here, I look at that as a function of the pressure on the system. And what we see is that as you vary the pressure over quite a number of decades, G over B remains roughly constant. This is what you expect for a crystal, and this is indeed what you see. In this region here, when we took this disordered case, and there's a single system, so it's noisier than the data when we did live averaging, but this is a single system, you see that G over B is going as P to the 1/2, which is what you get for the jamming behavior. So the question is, what's happening for this intermediate case? And what we see there is that the intermediate case is looking very much more like the jam system than the crystalline system, even though by eye you would have said this intermediate case looks by eye, by any structural measure, it would have looked much more like a crystal. Likewise, we can do the same thing with the density of states. So I remind you, this is what the perfect crystal looks like. This is what I showed you before for what the jam system looks like. And now the question is, well, what does the density of states of this intermediate system look like? And what that looks like is, again, this low frequency part is much more similar to what's happening in the jam system than it is what's happening in the perfect crystal. So as I get closer and closer to lowering the pressure, this thing begins to look much more like this. The high frequency stuff still retains some of the aspects of the high frequency of the crystal, but the low frequency behavior begins to look much more like a like jamming. And so the point of this is that, okay, so even though I told you about jamming as a, starting from this perfect disorder, it makes sense to want to know what the two extremes look like, because if we're going to try and understand the properties of this intermediate system that look kind of ordered to you, it would have been much easier to start from looking at it from a from the jamming perspective, the disorder perspective, rather than from the ideally crystallized system. Okay, so I've just told you something about these mechanical extremes. There's a crystal. It has this ratio of G over B. They're roughly comparable to each other. And they have plane waves as the low frequency excitations. In the jam solids, we found that G over B looks like it's going to 0 as you get close to transition. And instead of having plane waves, it has this new class of modes, anomalous modes, that are not there in the crystal. Yeah.
Is there any similarity between jam solids and glasses?
Yes. So look, how should I answer this? This is a big debate, right? I should be very careful that all I'm telling you about are at t equals 0, right? And so these are t equals 0 systems, and that makes life very much simpler to be able to understand things. If I were going to say, oh, this has something to do with the glass transition going from the liquid into the glass, there you have to worry about, well, what is temperature doing, and worrying about that. But if I want to ask, okay, so what are the properties of the low temperature phase, I think this is actually capturing a lot of that physics. And so I would say, yes, it does tell me a lot about what's happening in the glass phase, but I'd be careful about saying, okay, now we have to actually add temperature and do something serious with the temperature. Okay, so my point here is it doesn't take much disorder to behave like jamming. But now I want to ask, well, what else is distinctive about disordered matter? And so what I want to now ask is, that there's another principle I think is at work here. And so let me start with the crystals. And what do you think that you have in a crystal? So suppose I have a very simple crystal. So let's say a cubic crystal, right? So it's just particles at the corners of cubes. And I have bonds between each pair of particles. And I ask, okay, so let me compress this system and measure the shear modulus. I can do that. And now I go in and I grab one bond out at random, and I measure the modulus. And the modulus will have dropped by some amount, some small amount, because I've taken out one bond. But now I put that bond back, and I go someplace else in the crystal, and I pull out another bond. How much does that one change the modulus? And it changes the modulus by the same amount, because all of these bonds are doing exactly the same thing for what this crystal is going to respond for to some compression. So removing any bond, and you get the same change for the resistance of shear or the resistance to compression. That is, it doesn't matter which bond you take out. Another thing that you would kind of naively guess for this, or I would naively guess, I shouldn't say about anyone else, but my naive guess had been that if I take out one bond that happened to be very strong and important for the bulk modulus, I would have kind of guessed that that would have been an important bond for the shear modulus as well. That is, if it's an important bond in the crystal giving it its structural integrity, it's probably important for all sorts of different aspects of this. And so these are kind of what I expect for the behavior of a crystal in removing a bond, and how all the different bonds contribute to the elastic properties. And so it doesn't mean you can do very much with this. And so, as Somerset Maugham said, perfection has one grave defect, it's apt to be dull. And that's what's happening here. That every bond does the same thing, so you're not going to gain much from this. But how about if we did this for a disordered system? And so disordered matter is not similarly constrained. And so something different could happen here. And so this is what I want to explore. And so I'm going to just explore this in the in the following way. That is, if this was I'm going to make a spring network out of my jam system just so that we have something concrete to work with. So if these were my spheres that happen to be in this particular arrangement, what I'm going to do is each sphere I'm going to put a node at the center, and every pair of spheres that were overlapping I attach by an unstretched spring, and only those that are overlapping have an unstretched spring between them, and that's it. So we now have gotten rid of the spheres, we erase the spheres, and we now have a network just connected of balls and springs. And so this is the spring network that's starting from the jam configuration, and so this is the one that I'm going to be looking at. So here, the question is, well, if I were going to remove a bond from this jam system, what's it going to do? So I remind you what I just told you for the crystal. That is, if this is the probability that taking away bond I will change the bulk modulus by an amount delta B, it's going to be a delta function, right? Because I just told you that for the crystal, every bond does the same thing to the modulus. So taking any bond away does the same thing, so it's going to be just a delta function. They're all doing the average value. Okay, so what's going to happen if I have a disordered system? And so my naive expectation would have been, well, it would look something like this. That is, you would take that nice delta function and you'd spread it out. It would have somehow Gaussian smooth disorder. I mean, this is what this thing would be looking like. And so, is this what the jam system does? And you can do this for both delta B and delta G, that is the shear modulus and the bulk modulus separately. You can do each one of these separately. You can ask, what does this look like? And so, the first thing is that I'm going to show you this graph, but the first thing is that this is going to be a log axis, and this is going to be a log axis. So you can see that something funny is at foot here. It's no longer linear, it's going to be log-log, and this is the kind of behavior that you get. That is, both for delta BI and delta GI, when normalized by their average value, first of all, fall essentially on the same curve, but it's a very smooth curve. It goes over many, many decades, all the way down to the lowest value that we can find. At high values, it falls off. It has this functional form of y to the minus a half, e to the minus y. And so we can say a little bit why that occurs, but that's not the point that I want to make here. I want to make the point is that, first of all, we have a very, very, very broad distribution of how each bond contributes to the modulus. So some bond here contributes hardly at all, but there are a lot of them. A few bonds here, very small because it's low on the y-axis, have a very large contribution to the modulus. So that's what this curve is telling us. And now what I want to ask is, well, suppose I took this particle that was out here, that bond, and I removed it. It happened to have a very large contribution to the bulk modulus. What does it do to the shear modulus? It doesn't matter at all what its contribution to the bulk modulus was to the shear modulus. That these two contributions, even though these curves look almost identical, they're almost completely uncorrelated with one another. So what one thing does for the bulk modulus doesn't care what it does for the shear modulus, and vice versa. And so this, if you think about this for a second, this is something that you wouldn't have expected for the crystal, but it's true for a disordered system, for this jam system. And The other thing is, if you think about it, this allows you to now do something with this system that you didn't think you could do before. So what is it that I want to do? So remember this G over B. I told you about that early on. That G over B is a ratio of the shear modulus to the bulk modulus. It was roughly constant for all crystals, but now, and also this is what was important for telling me what the Poisson's ratio was for a system. So if I have G over B being very, very large, that means I have a weird solid. If G over B is very, very small, that's the normal solid. But now, since I can take out a bond that has a very small b or a very large b, I can control which of these bonds I'm taking away. And so if I take bonds out at random, then nothing happens to G over B. The system remains more or less the same. This is what you get in rigidity percolation, typically. That is the G and B both drop in tandem with one another. But now if we go and try something else, which is I'm going to prune only those bonds which have the maximum contribution to delta B. That means they do something just average to delta G. So by taking away the one with the largest delta B, I'm changing this ratio G over B and I'm making it grow. And so it grows. And again, I want you to notice that this is a log scale. And so this is 10 to the 12. So this is 12 orders of magnitude increased by taking away a few percentage of the bonds. I could do the other thing, which is I could have taken away the minimum delta B. And if I take away the minimum delta B, that means B isn't changing at all in this ratio, but G is dropping by an average value each time. And so this curve is going to fall. And so, between here and here, it's something like 16 orders of magnitude change. So I can go from something which is completely normal, that is completely incompressible solid, which is a normal solid, to something which is totally auxetic, which is Poisson's ratio, which is -1, which is the maximum it can be for an isotropic system. And you can play the same thing with the delta G as well. So you can get these different curves depending on which scheme you decide to use. So that means I'm able to start to make materials from this that I wouldn't have been able to make from the normal system. So this was for the global moduli. Is there anything else we can do? And so we wanted to ask, could we do something more local? And so the idea was we were looking at proteins, and the property of proteins is something that is called allostery, where if you take a protein, which is a big molecule, and you do something over here, you can make something over here on the other side of the molecule suddenly bind to a receptor or something that it needed to bind to. Whereas if this hadn't been there, this wouldn't have been able to bind. And so it is a way of controlling the behavior of the protein by doing something on one side and it acts on the other side. So what we wanted to find out was whether we could do this in our networks. And so here is a case where the idea is that I come in and I ask you, could you please come up and point to two nodes that you would like to be the source? So you come in and you happen to point to these. Then I ask you, please come in, tell me two that'll be the target. You point to those up there. This is totally at random, you got to choose. Then I ask you, do you want the target to go together or go apart when I pull on the source? And again, that was your choice. And we're able to, just by removing, I think in this case, there were something like 4 bonds difference between these two things, we can make either of these two things happen. We can make the source control multiple targets around the egg. So you can begin to do all sorts of functional materials by controlling one source or another source and make different things around this material begin to do what you want. So it's a kind of a metamaterial that you're able to start to control. And so then we make them in the lab, and so This is work that we've done. So this is a two-dimensional example. And this is a three-dimensional example that we can build on a 3D printer, that we can make these things. You squeeze them at one point, and they do what they want at some, what you want them to do at some faraway source. And so this is the kind of thing that we're able to do. And so with that, I want to kind of start to end up and say, okay, so what have I tried to tell you? I tried to tell you about something about this jamming, and about this is kind of a transition. It's a transition into a disordered state. It's not something that we have a whole lot of experience with. That is related, we think, to a lot of the theory that we heard here before about spin glass transitions. And so the glass transition, what you asked earlier about, that is, this is somehow a very simple cousin of that, that may be relevant because we can understand this transition at 0 temperature. You can understand the transition at infinite dimension, but at all temperatures. And so the interesting thing is in between at finite dimensions at finite temperature, and that's the part that we want to work on. But it's a mixed order transition. It has new excitations and a new kind of rigidity. It's intrinsically different from crystals in a number of ways. It has new features, and it's a starting point for even nearly ordered matter. That is, it's something that you want to know about how to begin to think about matter that's almost completely ordered. And then I told you about this principle of bond level independence that's allowing you to actually prune these things, make materials that have the function that you want to have them designed. And so this puts me in mind of this quotation from one of my favorite authors, Haruki Murakami. A certain type of perfection can only be realized through a limitless accumulation of the imperfect. And I think that is somehow a rather concise description of what we've seen. And so, look, I don't think any good talk should really end without the bullshit line. And so this is a bullshit line. And so what I hope is that you've believed everything above this line. I mean, I think I can defend all the stuff above this line. Below this line, okay, we can debate. And so what are the things that we hope you can do with this? Well, okay, so far I've designed all these materials on a computer and then been able to work with them, make them in the lab. I'd like to be able to do this in situ. That is, have the material tell me what it wants to do. And by measuring certain aspects of it, then go in and be able to prune the properties that we want. You can think that this is important for aging. I don't mean just aging like we're all getting old, but I mean like you have stones in a dam that are on top of each other. They're weighting on top, a lot of weight on top of it, and they're pushing hard on each other. It's a granular system, it's a jam system, but where they're pushing is under a lot of pressure, and those points are going to plastically deform over time. So what that means is that the ones that are under the most pressure begin to change. Well, that's just kind of like what we just told you about here, is that this is, if we do that, somehow the properties of this thing, it's not just the whole thing gets weaker, it's that it goes from being a incompressible system to one that's auxetic. And so that's a difference. Can you do this at a microscopic scale? That is, could you actually make a glass so that you could zap it with a laser to break the bonds that you want that are under strain? And so that's one type of thing. We'd like to go back to biology. We said that this allosteric stuff came from biology, but can we give anything back to biological sphere? And then the final thing I just want to point out as well, architecture these days is no longer really these rectilinear things. I mean, Frank Gehry does these things that are all over the place. And so you can really start thinking, well, you could start using these kind of jammed networks as a way of doing biology, doing architecture. So the architecture will be functional in a way. That is, if you're in California, you want these things to be able to withstand earthquakes, and so could you design something about how the building responds by putting that in? But for me, the more interesting thing would be if, I have my office and I have my colleague across the hall who's really irritating me. I'd like to be able to go to my window and stretch it a little bit and have his window fall out. And so this would be something that's now possible with this kind of a this kind of functional material that we've kind of designed here. That these things can be thought about at least, and we can imagine these. And so just to finish up, these are all the people who have actually done all the work on this. And so I should definitely point out, first and foremost, Andrea Liu, who has done every bit of this along with me. And so this has been completely joint work. And these have been the people who've worked with us. So Florio Hearn and Leo Silver were postdocs on the early work. Carl Goodrich and Daniel Hexner have been doing the stuff on the auxetic materials. Jason was working on the allosteric materials. And then Nidhi and Irmgard were the student and postdoc who have been doing the stuff in the lab and building these materials that we can make. Okay, with that, I want to thank you very much.
Questions?
There's a quick question. How many molecules in your simulation?
So, it varies from various things depending on what we're doing. But our largest ones have been maybe 500,000 when we're really trying to go to the very largest. To make these things in the lab, we're dealing with 1,000 or so nodes. That's a kind of thing that we would be working with so far.
Other question? Yes.
When you make a crystal in the lab, you're not going to get a crystal like the one in blue you show. That is a perfect crystal you show in all your slides. You get something with defects, dislocation, dislocation. That looks like a little bit your intermediate crystals. So do you think this jamming picture is actually relevant, or it is not to describe real crystal? There is something related to the...
So look, what I think is that it depends on, it's not every system that I make will this jamming be the right description of it. But it's one of the two poles between which the real system exists. So if you have a few defects, I certainly wouldn't think that this is where I want to start. But if I have a polycrystalline system with a lot of grain boundaries, then what we found is that these descriptions are not a bad way of starting that. So it really depends on how much disorder you're putting in here. And if you go to the real disordered limit, then yes, this is certainly a better place. But this intermediate range is, it's different aspects. As you saw even with that the intermediate one, with the normal modes. The high frequency still looked more like the crystal. It was the low frequency ones that began to look like the jam system. So you really want to know about both aspects.
Yes?
One of the things that sort of surprised me most, maybe you could explain it a little bit more, when you showed what happened when you started with a perfect crystal, and then if I understood it, you just removed a few sites, and I don't know whether you replaced them or what you did with them. You started with a pure crystal, and then you removed a few atoms or sites, and I'm not sure whether you replaced them or did something to them. And after a small number of these, you got a very big change in the shear modulus, as I understood it. I can understand that you might have things rattling around, and therefore you would get a big change in, there'd be a lot of low density things, but I would think they would be localized. And I'm not sure if could you explain why that would actually have such a big effect on something macroscopic like the shear modulus?
So look, I think that's a good question that is, and I don't think I have a great answer for it. What we've seen is that when you put the disorder in, when it gets into this intermediate regime, it kind of phase separates a bit. And so the disorder tends to be in in regions and crystalline systems being regions. And so that may be part of the reason why you have enough of this disordered region that begins to have that, for the shear modulus, that begins to take over. As I was saying to the other question, when you have polycrystalline systems, then it does the same thing. That is, the disorder is not kind of randomly in there. The disorder has some order to it. I mean, if you will. And
Right.
so I think those are some of the issues that.
Well, I understand the polycrystalline, but I thought that you were just removing bonds at random and that there was no correlation between the ones you were
That's right.
removing,
So
and
what
they were
we do
frozen.
is if we remove bonds at random, and then we put those particles up, not bond, we took particles out at random and put them back at random.
Well,
and
there's
now
no
the
place to
whole
put them if,
we just put them in at random, and now the system rearranges to its new lowest ground state. So if I took one particle out and I put it back in, it would be a vacancy dislocation pair. It would come here, it would relax around this area, it would relax around this area. When I take 1% out, now this thing is not going to stay particularly crystalline anymore because these particles are all interacting, so the system doesn't have to stay. You would not necessarily look at this thing and say, oh, that's still in the same position, because all the particles now move to go to their new ground state.
I see,
the
so
whole thing
it's a
is-
nonlinear thing where
it's
you
nonlinear thing.
rearranged actually a large number of things, enough so that it's like, even though it's at 0 time, presumably you're just relaxing always
To 0
downhill. You're never going up over any barriers, but
That's
still,
right. We're always going down.
but it can still rearrange enough.
And that's what makes life simple in
Yeah,
this.
yeah, okay, thank you.
Okay, let's take one more question over there. Yes.
So just a comment related to the last discussion. A somewhat similar phenomenon was noticed by Oded Schramm and company, mathematicians studying critical percolation models in 2 dimensions. If you take a critical percolation system in 2 dimensions, in a, say, a rectangular region, the probability that there is a connection from left to right is approximately 1/2, at least somewhere between 0 and 1, because not having it, you have a dual path, so that the two are more or less balanced at the critical point. And it was noticed that if you take a critical system, changing just a tiny fraction of the status of edges actually flips the answer whether there is a connection or not to an independent one. That's true only at the critical point. When you're off criticality, there is no such effect. That's work of Schramm and company.
I mean, so
Here he's starting from a crystal.
Though if you start from a crystal, what I said does not apply. But at the critical point, and I think the discussion is near the jamming transition, which resembles that.
Okay, so let me
It makes
just
a
make
difference.
one comment about rigidity percolation, which is what you're talking about, and jamming. I mean, jamming is not rigidity percolation. So that line that I showed you when we took things out at random, that would have been the way we do rigidity percolation, and G over B remained constant as we did that. When we do jamming, what we find is that G over B goes to 0 at the transition. It doesn't remain constant. And so it's a different class of phenomena than, I mean, I'm sure they're related, but it's a different, the critical behavior is really quite different.
Okay, let's thank the speaker again.